In the last lecture, we introduced the important concept of a potential because we made use of the fact that curl of E equal to 0 implies that E can be written as minus gradient of the scalar field phi, which is your potential. Now, if I were to write down the solution for phi, I would write it as phi of r is nothing but integral E of r prime dot dr prime, where the endpoint is fixed at r. Of course, I have to put a minus sign here because E has been written as minus gradient of phi. There is an ambiguity about the initial point, which we can choose to be any point, and let me denote it by r1. If I had an arbitrary vector field V, this particular integral on the right hand side would have depended on r1, it would have depended on r, and it would have depended on the curve. However, because curl of E is equal to 0, we know that it is independent of the curve. Therefore, this r1 is an inessential initial point. It only serves to define the 0 of my potential. The value of my potential at some particular point of r1, and with respect to that, we could determine the potential everywhere else. In other words, the potential is defined everywhere up to an additive constant. So, once we remember that, I also made a statement that we can, without any loss of generality, choose my potential to be 0 at r equal to infinity. So, phi of r equal to 0 at r equal to infinity. So, if we did that, we can immediately write my phi of r to be minus integral infinity to the point r into E of r prime dot dr prime. We also wrote an explicit expression for the potential, namely if you are given a charge distribution. So, what do I mean by that? Here is my coordinate system. Let us say that my charge is distributed in this particular region. Then my phi of r is simply given by 1 over 4 pi epsilon naught integral d cubed r prime over mod r minus r prime into rho of r prime. So, it is essentially a matter of choice whether you want to determine the potential directly given the charge distribution, or one would like to determine the electric field and then perform this line integral. And the point that I was trying to make in my last lecture, at the end of my last lecture, was that if you have a rather complicated charge distribution, for example, in this case, I did not specify the nature of the charge distribution. There may be no spherical symmetry, it might be behaving in a very complicated fashion as a function of r. It may not be representable as a simple function of r. Then it is much better to determine the potential first and then determine the field, because determination of the potential requires only determination of one scalar field, whereas the determination of the electric field requires the determination of three fields. On the other hand, if there is a symmetry like spherical symmetry or cylindrical symmetry, then it is better to determine the field first. The direction and the magnitude of the field gets easily determined by Gauss's law. Come back, do the line integral, which is very easy to perform, and then you can determine the potential. I was illustrating the latter situation where there is a potential, and the problem that I gave you was a very interesting potential, namely r of rho of r is nothing but k r to the power of n if r1 less than r less than r2. So, what we have is two spheres of radius r1 and radius r2. So, in the space between the two spheres, in that annular region, in that spherical shell, my rho of r has a behavior which is given by k r to the power of n. On the other hand, if r is less than r1, so if r is less than r1, then it is equal to 0, and likewise this was equal to 0 if r is greater than r2. What I asked you is to determine the field given this by making use of Gauss's law. I will not work it out, I will leave it as a problem for you, and once you get the field, all that you have to do is to integrate. The line integral is a fairly simple thing to evaluate, because E and the unit vector R are parallel to each other, because this is a spherically symmetric case, and therefore the field is radially inward or outward everywhere depending on the sign of the value of k. The next thing that I asked you is to look at this special case. There are two special cases which I was trying to list. One was n equal to 0 corresponding to uniform rho. Rho is uniform in the annular region, and the next one corresponds to R1 equal to 0, which corresponds to uniform rho throughout the volume of the sphere. So we can set R equal to R2 equal to R. These two are familiar examples, so you can specialize to this particular case. Check whether your answers agree with the standard answers which are given in any textbook, and then you can try to work out the consequences. Now, in order to proceed with my illustration, what I shall do is to consider another example, and that is of cylindrical symmetry. That example is very close to the example that I gave in the case of two spheres. In fact, I am going to write down exactly the same formula, except that the notation R means a slightly different thing. So what do I mean by that? What I shall do is to consider, let us say the z-axis here, and let me consider an infinite cylinder. What do I mean by infinite cylinder? I mean it's a very long cylinder, and I am looking at distances from the axis of the cylinder such that the length of the cylinder is very large compared to the distance. We have explained these things in great detail. So this is a cylinder of radius R1. Now what I will do is I will consider another concentric cylinder, which is a cylinder of a larger radius. So let me write it here. So this is a concentric cylinder, coaxial. It is the same axis that is there. So this is a cylinder of radius R2. What I now do is to fill the space between the two cylindrical surfaces with a charge density. So rho is not equal to 0 here, and of course in this region rho equal to 0, in the outer region rho equal to 0. So this is an example where my rho is existing only in between the inner cylinder and the outer cylinder. So let us employ the same formula again. So I have the radius R1 and I have the radius R2, the distance of the surfaces of the cylinder with respect to the axis. Therefore again I will write rho of R is equal to k R to the power of n if R1 less than R less than R2 and equal to 0 elsewhere. So you see, the problem is paralleling the earlier problem of spherical symmetry. You have to construct a Gaussian surface involving cylinders and not spheres in this particular case. The only care that you have to take is that you cannot choose my potential to be 0 at infinity. Because I have taken the cylinder to be infinitely long, what we have to remember is that my field goes like 1 over r for large values of r. As I go farther and farther away from the axis, my potential therefore goes like logarithmic of r. And we know that logarithm r is an increasing function of r. Therefore, it is impossible to choose the potential to be 0 at infinity. If I did that, my potential would be divergent at all points in the finite regions of space that we are interested in, and we would not be able to do any calculation. Therefore, it is convenient to choose the potential to be 0 with respect to some other point. And one convenient point perhaps is to choose the surface of either the inner cylinder or the outer cylinder. I will leave it for you people to choose the way you want it to be. Once you did that, you can determine the potential in the inner region, in the intermediate region, and in the outer region. The important point that you have to notice is that the choice of your potential dictates the value of the potential in the inner region. What do I mean by that? The choice of the 0 of the potential. I have to fix the value of the potential at some particular point. So let us say that there is a special point which I shall call as Rs, at which I will say this is equal to 0. Once I did that, there will be a uniform potential between 0 and capital R1 for the value of R, and that will give us what the potential, the value of the potential inside the inner cylinder is. And then of course the potential will be a function of R as we come to the interspace between the two cylinders and also when we go outside. So I will request all of you, I will urge all of you to solve this problem as well. Now, having worked out these problems, we have discussed various problems. I first looked at the dipole, then I introduced the problem of quadrupole. I have introduced charge distribution between two concentric spheres. I have introduced charge distribution between two concentric cylinders. Now, let us determine two matters of principle and explore the meaning of the potential a little bit more. Now, I am not interested so very much in the potential as much as the potential energy. So, let me spend some time on the concept of potential energy and let us see what we can say about that. Okay. You see, suppose there is a certain charge distribution. So, without any loss of generality, I will choose the charge distribution to lie in this region. So, let me call it as R, the region is R and the charge is non-vanishing in this particular region. Obviously, we are interested in finite charge distributions. Now, here is a generic point P with a coordinate R. What I am going to imagine is that I am going to bring a test charge Q at this particular point and I ask what is the potential energy of this test charge Q because of the field produced by rho, which is not equal to 0 in this particular region. The answer to that has already been written by us and we know that the potential is simply given by Q into phi of R. Now, although it might appear to be sort of repetitive to you people, I am going to spend some time belaboring the same point and that is the following. This potential is the interaction energy between the charge Q and an external field phi of R. What do I mean by external field? By that I mean this field phi of R is produced by the charges which are sitting in this region. Q is not to be counted to be one of those charges. So, if you feel like I could have constructed a larger region, so let me indicate here, I could have constructed a larger region like this and I could have said there is a charge density in this particular region, in which case Q would have been a part of the system. No, I am not doing that. What I am interested is in the interaction potential energy between the charge Q and the rest of the charges which are localized in this particular region and we are writing V equal to Q phi of R. Now, in order to make it notationally clear, I want the notation to exhibit whatever I want to say. I will call this charge as Q1 and I will call this rho as rho 2. By that I mean it is in a different region, the second region. This is the first region if you feel like. My region is also R2, therefore this will be, my V can be written as Q1 phi 2 into R. I hope everyone understands what I mean. What I mean is that the charge Q1 is seeing the potential produced by the distribution 2. Of course, the potential is produced at the location of the charge Q1. That is the statement that we are making. So, perhaps I can even make this point R1. I will make the point R1. Charge Q1 is always located at R1. So, once I write this potential, since I know how phi 2 is produced by the charge distribution, I can now write my V to be 1 over 4 pi epsilon naught, okay, d cubed R2. d cubed R2 is this region R2, the volume contained in this region R2, and we are going to write mod R1 minus R2 rho of R2 is what I have, and of course I have to multiply it by Q1 which is located at R1. So, we have been able to write a nice expression where the notation makes it clear the kind of physics that I want to do. So, let me repeat that expression. V of R1, which is the location of the charge Q1, is simply given by Q1 over 4 pi epsilon naught d cubed R2 mod R1 minus R2 into rho of R2. This is the first step in our calculation. Now we can generalize our situation a little bit more. What we can do is to, let me draw the figure again. I have my charge distribution in this region R2 and I had a single charge here. This single charge, let me spread it around in this particular region. Let me call it as a region R1. In other words, I don't have a point charge in the region R1. I have an extended charge. Therefore, I have to calculate the potential at every point R1 in the region R1 and I should perform an integration. And of course, every point R2 in the region R2 is going to contribute. I am not going to spend too much time insulting your intelligence by trying to derive the expression. Let me write it straight away. We all know that in that case, my potential, the interaction potential, I can write it as between 1 and 2. 1 is a charge distribution which is sitting here. 2 is another charge distribution that is sitting here. This is nothing but 1 over 4 pi epsilon naught integral d cubed r1 d cubed r2 divided by mod r1 minus r2 rho 1 of r1 rho 2 of r2. Please notice how careful I have been. I am saying there is a certain charge distribution rho 1 at r1. There is a certain charge distribution rho 2 at r2. There are two independent charge distributions and the interaction energy is given by this. Of course, this can be written equivalently in yet another form. So this can be simply written as d cubed r1 rho of r1 phi 2 of r1. Why? Because integral d cubed r2 rho 2 of r2 divided by mod r1 minus r2 with the factor 1 over 4 pi epsilon naught is simply going to give me this expression. And because of the symmetry, we see that this is also equal to d cubed r2 rho 2 of r2 phi 1 of r2. So we are saying this is the same as V21. The energy of the charge distribution 1 because of the 2 is the same as the energy of the charge distribution 2 because of the 1. Therefore, depending on the situation, depending on the nature of the problem, you can either use this expression or this expression in order to define the or evaluate the potential. All of them are equivalent expressions. At a later time, after a while, I am going to work out a few examples where I am going to use different expressions in different situations. But now, let me continue my theme in order to rewrite my potential in yet another different form. So let me start with the expression for V12. What was my V12? My V12 was written as integral d cubed r rho 1 of r phi 2 of r. I have removed the notation r1 because it is understood. Therefore, if you want, I can even keep this. Now, I know that there is a certain charge density rho 1 and whenever there is a charge density rho 1, it produces its own electric field. So, we ask the question, is it possible to eliminate all references? Please notice what I am saying. Is it possible to eliminate all reference to the charge and write the potential entirely in terms of the field? That is the question that I am asking. This in fact is an important question because at a later time when I discuss electromagnetic field, we are going to argue that the energy resides in the field even in the absence of the sources. So as a kind of warm up, as a kind of preparation to whatever we are going to study, let us say in after another 6 or 7 lectures, let us ask how I go about writing the expression V12 entirely in terms of the fields. The answer to that is very, very simple because I know that by Gauss's law, divergence E of R1. Obviously, the divergence is with respect to R1. The derivative is with respect to R1 is nothing but rho 1 of R1 divided by epsilon naught. This is my Gauss's law. That is how I started the discussion of the whole subject. So, what I shall do is to replace rho 1 of R1 by epsilon naught divergence of R1. If I did that, what do I get? I get V12 is simply given by epsilon naught integral d cubed. So this is an R1 which is sitting here. D cubed R1 divergence of E1 of R1, because this is the field produced by what I call the charge density labeled one, E1 of R1 into phi 2 at R1. So 1 and 2 clearly tell us that there are two distinct different charge distributions that we are interested in. Now whenever there is a differential operator of this particular kind and whenever there is a volume integral, what do? We write the integrand as a total derivative, convert it into a surface integral and then look at the other term. So let me do that. So I am going to write this expression as epsilon naught d cubed R1 is what I have. I will write a gradient outside, divergence outside, and write E of R1 phi 2 of R1 and close the bracket. So in doing that, I have added an extra term. Therefore, I should write down the difference between the two terms. And what is that term going to be? This is nothing but minus epsilon naught d cubed R1 E of R1 dot gradient phi 2 of R1. This is a very, very neat expression. So what have I done? I have written my potential energy, the interaction potential, as a first step by eliminating rho. I have an electric field sitting here, I have the gradient of phi sitting here, which is nothing but the electric field again, and then there is a total divergence term. Now let me examine each of these terms and see what it means. What was the first integral? The first integral was simply given by epsilon naught divergence E of R1 phi E1 phi 2 of R1 into d cubed R1. This integration is over the whole space. But then Mr. Gauss comes and tells us, look here, you have the divergence of a vector field. My electric field is a vector field. My phi is a scalar field. A scalar multiplying a vector gives me a vector. Therefore, by Gauss divergence theorem, this can be written as a surface integral. Therefore, this is nothing but integral a surface. What is that surface? E1 R1 dot ds1 into phi 2 of R1. It does not matter how we split this integrand and the integrating variable. This is what I have. And since the integration is over all space, this surface integral is evaluated in the limit R1 going to infinity. Please remember that we are discussing matters of principle. We are not looking at some idealized case. Therefore, we are necessarily looking at fields which die as we go to infinity. Finite charge distributions produce fields which go to 0 as r goes to infinity. My potential can either go to 0 or a constant depending on the choice of the origin. Therefore, this integral goes to 0 as r1 goes to infinity. Therefore, this integral is identically equal to 0. The first integral cancels. It becomes 0 because of the Gauss divergence theorem and because of the property of the electric field. Therefore, my potential energy between the two charge distributions is simply given by minus epsilon naught d cubed R1. I had E1 of R1 dot gradient phi 2 of R1. The gradient of the potential at the point R1 produced by the charge density rho 2, the distinct physical system. But then we all know what gradient of phi 2 is. This is nothing but epsilon integral d cubed R1 into E1 of R1 dot E2 of R2. My R2, which is the integrating variable, is a dummy. Therefore, I can always replace one dummy by another dummy. I will write V12 is equal to epsilon naught d cubed r E1 dot of r dot E2 of r. So this is another famous expression, popular expression, much often used expression in order to determine the potential energy between two distinct charge distributions. So we can write the potential energy entirely in terms of the charge densities, or you can write the potential energy in terms of the charge density multiplied by the potential. There are two options there, and the third option is to write the potential energy entirely in terms of the fields. All these expressions in electrostatics are equivalent to each other. We can use any of them depending on the convenience of the situation, but later we will find that these expressions acquire a special meaning. That is something that you have to keep in mind at this particular point. Therefore, it is good actually to solve the problems that I give you using all these techniques to the extent possible. Now, having done this, let me look at yet another concept of potential energy. This is a more encompassing concept. So now we are going to ask what is the total potential energy of a given charge system. This is a slightly more generalized idea, and let me start by illustrating that with the simplest of the examples. What is the simplest of the example? Let me take a coordinate system and let me locate points R1, R2, R3, R4, Rn. So there is a charge Q1 here, Q2 at R2, Q3 at R3, Q4 at R4, Qn at Rn. So this is R1, this is R3, and this is Rn. From mechanics, we know that the total potential energy of the system is written by the sum of the potential energies of different pairs. Since there are n charges, there are n choose 2 pairs, and we have to write the sum of the potential energies of all the pairs. In order not to get into any confusion, I will use a different notation now. I will write the total potential energy as U. So how does it look like? The potential energy will be simply given by 1 over 4 pi epsilon naught, and I will write I less than j Qi Qj over mod Ri minus Rj. We know that the sum of the kinetic energies of the n particles plus these n choose 2 terms is a conserved quantity in electrostatics, so long as of course we ignore the magnetic field. This is what I have. Now I have put I less than j because I do not want to double count, but many a time we don't want to make such a distinction because that would mean ordering my charges. So I simply want to make a statement I not equal to j, but then there will be double counting. So the way to avoid the double counting is to rewrite it as 1 over 4 pi epsilon naught. I put a factor of half here and I write I not equal to j Qi Qj over mod Ri minus Rj. So here we are asking the question as to how much work we are going to do in order to what? Bring in and assemble n charges at points R1, R2, R3, etc. Rn. That is the question that we are asking, and we have got this expression. This is the total energy of the system. Now it is again straightforward to write down the generalization when I have a charge density. So how do I go about writing the charge density? My Qi will be replaced by one charge density, Qj will be replaced by another charge density. Therefore, it might appear that the generalization is straightforward. What do? We simply write it as 1 over 4 pi epsilon naught. I have a factor of half. Now my Qi and Qj will get replaced by the appropriate charge densities multiplied by the small volume elements. So I will write rho of R1, rho of R2 mod R1 minus R2 d cubed R1 d cubed R2. This is the expression that I have. So it appears that just as we were able to write down the interaction energy between two charge densities, but I did not ask how each of these charge densities was constituted. What I have done is to look at the interaction between amongst n individual charges. I have written it as a discrete sum, smeared each of these charge densities to occupy finite regions in space. I am not asserting that they are occupying disjoint regions in space, and I got the expression 1 over 4 pi epsilon naught half rho of R1 rho of R2 mod R1 minus R2 d cubed R1 d cubed R2. Every single step here appears to be completely straightforward. However, this is an example which tells us that we should exercise great care while going from the discrete limit to the continuum limit, because this expression means quite something different compared to the expression that we have derived earlier. Now, in order to illustrate that, again let me make use of Gauss's law and let me proceed step by step. So, what was my expression for the energy density? I wrote it as 1 over 4 pi epsilon naught. I have the factor half sitting here, d cubed R1, d cubed R2, these are the volume elements, mod R1 minus R2, rho of R1, rho of R2. Notice earlier I was very careful. I used to write rho 1, rho 2. I am not doing that. I have written rho of R1 and rho of R2. Now we all know the expression for the potential produced at a point R1 because of the charge density. This is nothing but half integral d cubed R1, that is what I have, rho of R1 phi of R1. In writing this, we have written down the potential coming from all possible sources. I am not saying that one particular charge distribution is external to another particular charge distribution. Now, all that remains for us is to write down the expression for entirely in terms of the fields by eliminating rho. I did that just now using Gauss's law. If you did that, you will get epsilon naught by 2 integral. I can replace the dummy R1 by the dummy R, d cubed R E squared mod E squared into is what I am going to get. So let me remove this and put the bracket here. So rho will be written as divergence E into epsilon naught. The divergence will be brought here. The gradient phi will be nothing but E. Therefore, I will get d cubed R mod E squared. What is the important statement that I am trying to make? Let me illustrate. When I wrote the potential, I wrote it as epsilon naught integral E1 dot E2 d cubed R. This was the interaction energy between two charge densities. Whereas, when I looked at the total energy of the system, irrespective of what came where and how it came, without making a distinction between something external to the other, I got the expression epsilon naught by 2 d cubed R mod E squared. Obviously, the two expressions cannot be the same. V can be positive or negative depending on the relative signs of E1 and E2. For example, if you have 2 point charges, one of them positive, another negative, we know what V is. It is minus Q1 Q2 divided by R, the distance between them. If there are 2 positive charges, V would be positive, but U we find is always greater than 0. In fact, this is equal to 0 if and only if my electric field is vanishing all over the space, that is, there are absolutely no charges. Therefore, we have to ask ourselves what indeed is the relation between U and V. The answer to that is very, very simple. What we do is to simply write my rho to be rho 1 plus rho 2. So, depending on the system of interest, I split my rho to be rho 1 plus rho 2, in which case my electric field by the linearity of the Coulomb law will turn out to be E1 plus E2. What am I doing? I am writing my U in terms of E. Therefore, if I write the total charge energy to be d cubed R, U of R. What is my U of r? This is my energy density. My U of r is nothing but epsilon naught by 2 mod E squared, which is nothing but mod E1 E2 whole squared, E1 plus E2 whole squared. And now if I were to expand this, what am I going to get? I will get a U1 of r. U1 of r is the energy density because of the field, because of the charge density rho 1. U2 of r is the field energy because of the charge density rho 2, because I will get a mod E1 squared plus mod U2 squared. Now comes the interesting term, that is epsilon naught E1 dot E2. And what does this expression tell me? Epsilon naught E1 dot E2 was indeed V. Therefore, I can write my total energy U to be U1 plus U2 plus U12, and U12 is identically equal to V. U1 plus U2 plus V. So, please realize that depending on the context, either I can ask for the total energy of the system, or I can ask for the interaction energy. They have distinct physical meanings. They have distinct physical interpretations. Sometimes we are interested in the interaction energy, which is always finite, which can be positive or negative, whereas the total energy is always a non-negative, in fact positive definite quantity for any charge distribution. So, I think this has been a rather comprehensive introduction to the concept of a potential and a potential energy. What remains for us is to work out a few examples. So, let me start discussing those examples, and after that I shall introduce the concept of a dielectric and a conductor, and let us see how we can exploit the physics even more. That of course is a rather complicated subject, because once we introduce the concept of a medium, we have to carefully introduce the concept of a time averaged, space averaged field, but that will come later. But now let me start with some of the simplest examples. The simplest example that I will consider is the case of two concentric spherical shells of negligible thickness. So, I have a sphere of radius r1 and there is a concentric sphere of a radius r2. This is a concentric sphere of radius r2. The inner sphere has a charge density sigma 1. Sigma is the surface charge density. So, this is the surface charge density. And the outer sphere has a surface charge density sigma 2. So, what we are saying is that sigma 1 and sigma 2 are constant, either positive or negative. So, what about the total charges? Well, I know what my total charge is. My Q1 is nothing but sigma 1 into 4 pi r1 squared. 4 pi r1 squared is the surface area of the inner sphere, and my Q2 is nothing but sigma 2 into 4 pi r2 squared. This is a very simple example. Then we can go to more complicated examples later. I will give them as problems to you. But this problem has enough generality to illustrate all the principles that I want to tell you. Okay. Now we can ask ourselves, what is the total energy of this particular system? And then we can ask ourselves, what is the interaction energy between the inner spherical shell and the outer spherical shell? So, this is each of them is a sphere of of zero thickness, is that okay? And all the charges residing on the surface of each of the spheres. Again, Gauss's law comes to our great rescue. It allows us to write down what the fields are. So, let me write down the fields. My electric field is equal to 0 if R less than R1. Everyone will agree with me. This is equal to Q1 over 4 pi R squared R if R1 less than R less than R2. In the region R greater than R2, again by Gauss's law, let me write it at a farther distance, Q1 Q2 divided by 4 pi epsilon naught 1 over R squared R hat. I missed the factor 1 over epsilon naught here. So let me introduce. So these are the fields and this is nothing but E1 plus E2. E1 is the field due to Q1, E2 is the field due to Q2 and we are looking at a point R greater than R2. What is it that we find? We find that the total charge Q1 plus Q2 contributes. We cannot make a statement that some of the charge is distributed in the inner sphere, some of the charge is distributed on the outer sphere. No experiment done outside will be able to tell us. That is what it is. Now the determination of U is a very simple thing for us because I have already obtained an expression for U. What was it? It was simply given by epsilon naught by 2 d cubed r mod E squared. I have an expression for E, therefore let me start integrating this expression straight away and see what I am going to get. So let me proceed doing it slowly. I have got an epsilon naught by 2. My electric field always came with a factor 1 over 4 pi epsilon naught. Since I had mod E squared, I am going to write 1 over 4 pi epsilon naught, 1 over 4 pi epsilon naught, 1 over 4 pi epsilon naught squared. Since my field is spherically symmetric, it is radially outward. In this d cubed r, I can perform the surface integral independently. Therefore, my integral d omega is going to give me a 4 pi and now I am left with the radial integral to perform. So let me open a bracket here and start looking at the radial integral between 0 and R1. So what was my R1? My R1 is the inner sphere. So in this particular region, so what I have is in this particular region, my field is identically equal to 0. Therefore, I am interested in the region R1 to R2. So let me write R1 to R2. I had Q1 squared divided by R to the power of 4 R squared dr. That is the expression that I have, because the field is exclusively coming from the surface of the charge on the inner sphere and the surface on the charge distribution on the outer sphere is not going to contribute. Now comes the next thing, between R2 to infinity, both Q1 and Q2 contribute. Therefore, this will be Q1 plus Q2 whole squared divided by R to the power of 4 R squared dr. This indeed is my expression for the total energy. This is finite. So everything is well defined and we can evaluate the quantities precisely. So if I were to do this, there is a 4 pi epsilon naught and a 4 pi epsilon naught which cancel each other. So let me do that in the first place. This is nothing but 1 over 4 pi epsilon naught. There is a factor of half. So let me open the bracket and let me try to integrate this expression. So let me write my Q1 squared first. I have 1 over R squared dr between R1 and R2. All of you are great experts in solving this. This is nothing but 1 over R1 minus 1 over R2. This integral is nothing but 1 over R1 minus 1 over R2. dr by R squared is minus 1 over R. Therefore, the lower limit and the upper limit, they will switch. This is the expression that I am going to get. And what is the next expression? The next expression is nothing but Q1 plus Q2 whole squared divided by 1 over R2. The surface at infinity, of course, is not going to contribute, because when R goes to infinity, 1 over R goes to 0. So this is indeed an expression in a very beautiful form, because it is clearly exhibiting my U1, my U2 and U12, which is nothing but V. So let me look at the expressions again. So let me write my total energy to be U1 plus U2 plus U12. How do I identify U1, U2 and U12? U1 comes exclusively from Q1. That is, if I put Q2 equal to 0, I get the contribution U1. U2 comes exclusively from Q2. If I put Q1 equal to 0 in the previous expression, that will be the energy of the outer sphere, the charge of the outer sphere. U12 involves the cross term Q1, Q2. So let me go back to my previous expression. Look at this. and write down U1, U2 and U12. If I look at Q1 squared, I have 1 over R1 minus 1 over R2. Q1 squared has plus 1 over R2, the R2 term cancels. So let me come back here and let me write U1 is nothing but half 1 over 4 pi epsilon naught Q1 squared by R1. That is what I have. The R2 term cancels. What about U2? Well, in order to write down U2, let me again go back to the previous expression. I am going to put Q1 equal to 0. Q2 squared is what I have. I am going to get 1 over 4 pi epsilon naught half with a factor of R2. That is indeed the correct expression. Therefore, this is nothing but 1 over 2, 1 over 4 pi epsilon naught Q2 squared by R2. Now we have to write down the expression for U12, which is the same as the V, the interaction energy between the two spheres, two spherical charge distributions. So let me go back to this expression, and what do? I ask for the cross term between Q1 and Q2. I get a 2 Q1 Q2 that cancels this factor of 2 in the denominator. Therefore, I will get 1 over 4 pi epsilon naught Q1 Q2 divided by R2. So in one shot, we have been able to determine the energy required to assemble a certain charge Q1 on the surface of a radius, on the surface of a sphere of radius R1. Then I ask, what is the energy required to assemble another charge Q2 on the surface of a sphere of radius R2? They are two independent problems, and we have U1 and U2. U1 does not refer to U2, U2 does not refer to U1. But now I say that these two are concentric spheres, and I ask, suppose there is already a certain charge density, let us say corresponding to the inner sphere, and there is a charge density corresponding to the outer sphere, what is the interaction energy? And that turns out to be Q1 Q2 by R2. Now this expression for U12, there is something funny about it, and that is there is no reference to R1. So this is indeed surprising. Normally, when we wrote down the expression for the interaction energy, we wrote Qi Qj divided by mod Ri minus Rj. It has to depend on the separation of the two spheres. It has to depend R1 and R2, that is what we would have expected. But however, when we looked at this expression, when we derived this expression, what are we finding? We are finding that it is a function only of R2, it does not refer to R1 at all. Now, is it possible to understand this expression? Well, there is nothing very surprising about that, because remember, V can also be written as integral rho of R phi of R d cubed R. So in writing this expression, I am actually referring to the inner sphere, rho corresponding to the inner sphere. And what is the potential due to the outer charge? The potential due to the surface charge density sigma 2 is constant. That is the most important word, is constant inside the sphere, inside the outer sphere, that is when R less than R2, when R is less than R2. Now we fixed our potential to be 0 at R equal to infinity. This has to be a constant, and by the continuity of the potential, we know that phi is nothing but 1 over 4 pi epsilon naught Q2 by R2. This is a constant. Integration rho of R d cubed R is the same as integration sigma of S ds, because it is defined on the surface. That is going to give me the total charge Q1, which is the reason why my interaction potential V is independent of R1. In fact, one can make a stronger statement, and that is something that you have to notice. So imagine the following situation. I have a sphere. I have a sphere of radius r and there is a uniform charge distribution sigma on this. What I do is to take the interior of the sphere and I put a very complicated charge density. I put a very complicated charge density rho of r. The only restriction is that rho of r not equal to 0 if and only if r less than capital R. Now, the above analysis clearly tells us that the potential is always given by V is simply given by, so I have to employ notation, that is, let me write it down and explain it, 1 over 4 pi epsilon naught Q1 Q2 by R. So sigma is going to give me a total charge Q2. The total charge Q1 coming from rho is given by Q1. It is given by 1 over 4 pi epsilon naught Q1 Q2 by R. It is completely independent of the nature of the distribution, of the shape of the distribution, whatever the volume may be. It might be as complicated as you feel like, but still the potential is given by this. Please remember this expression, because it is expressions like this that are useful later when we try to define the concept of a capacitance for conductors. So here we have an interesting problem which tells us what the meaning of a potential is and how to distinguish between the total energy of the system and also the interaction energy. Now there is another classic textbook example. I would like to work it out not so very much because of the mathematical complication. In fact, it is a very simple problem, but because of the richness of the physics that is involved in it, and that is the following problem. What we shall do is to consider a sphere of radius r, and now I am going to look at a rho of r which is equal to constant if 0 less than r and equal to 0 everywhere else. So this constant is equal to rho. That is what we are saying, some number rho. Obviously, my rho is simply given by charge divided by the total volume, and the volume is 4 by 3 pi r cubed. Therefore, this is nothing but 3q over 4 pi r cubed. This is my rho. Now let me ask myself, what is the total energy of this spherical charge, spherical distribution of the charge? You can imagine it to be some kind of a spherical droplet. Is that okay? It's a small drop. The answer is very simple. The total energy is simply given by epsilon naught by 2 integral mod E squared dr, d cubed r. So this integration obviously is over the whole space. However, in order to determine my E, I need the field in the interior region and I need the field in the outer region, which I will derive by using the Gauss's law. So let me start with the expression. E into 4 pi r squared, as usual, is the charge enclosed. So how do I write that? It is total charge enclosed divided by epsilon naught. I have my 1 over epsilon naught. My rho is nothing but 3q over 4 pi r cubed, because 4 by 3 pi r cubed is my total volume, 3 cube over 4 pi r cubed. And now I have to integrate it up to a point r, because I am interested in the region r less than r, and that is going to give me 4 pi by 3 r cubed. So this is indeed the expression for the electric field. So what do I conclude? I conclude that my electric field is nothing but, all my 4 pi's cancel, 3 cancel. So I have q over 4 pi epsilon naught. I have to be careful now. I am going to get r divided by r cubed. So in the interior region, my electric field is given by q r 4 pi epsilon naught r cubed if r is less than r. So this, you see, is a parabolic potential, and if I imagine that the q is positive, if I bring a negative charge, it gives you a confinement. My potential energy looks like r squared, the simple harmonic potential. If you move away from the origin, the field of course equal to 0 at that point, there is a minima at r equal to 0. So what is my field? My field is nothing but q over 4 pi epsilon naught r by r cubed if r less than r, and this is equal to q over 4 pi epsilon naught r by r squared if r greater than r. Notice that the field is continuous at the point r equal to r, capital R. Now we are in a position to evaluate this integral. So let me not spend too much time evaluating the integral. We have already performed such integrals. Let me give you the result. So believe me, go back and verify. What I am going to get for u is nothing but 3 over 20 pi epsilon naught q squared by r. This indeed is the total energy that is required to assemble charge in a certain volume V, and what is that volume? That volume is given by a sphere of radius r and the total charge is q. So we have this much energy which is given to, which is required in order to assemble that. Now all of you have heard of the name of Lorentz. Lorentz was a very bright man. He had already learnt relativity. So we are introducing a concept of relativity right now. And what does relativity tell us? It tells us associated with every energy there is a mass, and associated with every mass there is an energy. So this means that there is a certain mass because there is a certain electrostatic energy. So in order to emphasize that, let me put EL. That means there is a certain electrostatic energy. There is an associated electrostatic mass. So what do? I write U electrical is equal to M electrical C squared. So this means that my mass, there is a certain mass associated with M electrical C squared, but then I already know that there is a certain mass associated with a charge distribution because we have not yet seen charge without any mass. Is that okay? Electron, proton, neutron, etc., etc. Therefore, what we shall do is to consider a simple case. The simplest case is to consider the application to the electron. That is what Lorentz did. So what we shall do is to look at application to the electron. So what shall I do? I shall now specialize this application. So U electromagnetic was 3 over 20 pi epsilon naught q squared by r. This is a generic expression. Now consider an electron. What Lorentz says is that corresponding to this energy, there is an electromagnetic mass which is given by U electrical divided by c squared. It has the dimension of the mass. But on the other hand, if I consider an electron, it has its inertia, the usual mass, which is given by 0.5 MeV by c squared, roughly 0.5111, whatever, doesn't matter about that, 0.511 mm squared. And suppose I take an electron and put it in an external field, what happens? My electron moves because of this inertia. When the electron is moving, of course, it is dragging this much energy along with it. The electrostatic energy is also moving, q squared by r. So how many kinds of energies that we are going to write? How many kinds of masses are we going to write? So with a stroke of genius, Lorentz said, let us identify this inertial mass with the electromagnetic mass. So now we are trying to do some physics which goes beyond electrostatics that we are doing. We want to argue that my electron has a mass because it has a charge. But the minute I do that, I know that my m is fixed, my q is fixed, epsilon naught is fixed, the only free parameter is r. Therefore, the question is, what then is the radius of the electron? So this is the question. What then is the radius of the electron? Well, let us plug in the expression. I ask you to go back, look up the table and write down the expression. If you did that, my radius of the electron will turn out to be roughly 10 to the power of minus 15 meters. So it is of that order, 10 to the power of minus 12 to minus 13 centimeters. So up to order of 10 to the power of minus 4 to 10 to the power of minus 15 meter. And indeed, if Lorentz is right, then we should be able to perform an independent experiment to see that my electron has indeed a radius of this particular kind, and this is called classical electron radius. Unfortunately, this idea does not work. This idea does not work because I gave this information to you some time back. We know that the radius of the electron is less than 10 to the power of 19 meters. That is what the experiments tell me. So, electron cannot be looked upon as a marble, like a rigid marble, where there is a certain mass distribution and there is a certain charge distribution. If at all it has a radius, it is less than 10 to the power of minus 19 meters. Perhaps it is less than that. Perhaps it is a point particle. And now notice, as my radius goes to 0, my energy goes to infinity. It bloats up, and this is the so-called self-energy problem. Now, I am mentioning this to you because this does not mean that these ideas are not useless. Actually, since I have brought in relativity, I have brought in C and all that, this example goes to show the limitations of our classical mechanics. If we do a more careful analysis, we can argue that quantum mechanics must become important around 10 to the power of minus 15 meters. My electron cannot be described in terms of simple electrostatic phenomenon. That is something that those of you who are interested in physics will take up later. I need not worry about it at this particular point, but this is one illustrative point that I wanted to tell you. Okay. Now, to summarize the last 2 lectures, what have we done? We have introduced the concept of a potential because of the curl-free nature of the field, and what we have done is to exploit Gauss's law and show how potential can be evaluated. I have also told you how, when the charge distributions do not have a simple form, it is easier to determine the potential and then go on to determine the field. That is something that I have told you. And then we made a distinction between the total potential energy of a given charge distribution and the interaction potential energy between 2 different charge distributions, and we have worked out a simple electrostatic case. Now, if we want to proceed further, we should now give up this kind of a toy model example and look at real physical systems. In real physical systems, we cannot keep on dictating this is the charge distribution, that is the charge distribution. Once I have a charge distribution and I bring in another charge, the charge distributions rearrange themselves because of the interaction. As to what kind of a rearrangement takes place, whether the charges are completely free to rearrange themselves or whether they are not completely free to rearrange, this goes by the subject of electrodynamics in a media. If the electric charges are not completely free to rearrange themselves because of other interactions, the electrons are bound to the lattice, they are called dielectrics. If the charges, at least a fraction of the charges, are free to move and rearrange themselves in an external field, those are called conductors. So, the real importance of the concept of a potential, this charge distribution, comes when we discuss conductors and potentials. Indeed, an interesting physics idea. Since we are running out of time, we shall explore that in the next lecture.